We're going to get started this afternoon by introducing you to Chris Kucharik, Professor and Department Chair of Agronomy here at UW-Madison. He's going to take us through an overview of agriculture, nitrogen, and water quality in the state. Come on up, Chris. Let's see what you got.
Thank you, Pam, and good afternoon, everyone. It's good to be here, and I appreciate the invite to come talk to you and sort of set the stage as we start about some of these key issues affecting Wisconsin agriculture. I hesitated whether to even put this slide up. Obviously, everyone understands the importance of agriculture to Wisconsin's economy, but more so, think about the diversity of agriculture that we deal with in a state that has a wide vast of land use and land management. And the key thing about our agricultural crops is the amount of fertilizer that we rely on to help sustain and boost yields. This graph, which was put together by a student in my lab who has an appointment at UW-Stevens Point, is showing the recommended amounts of fertilizer for common crops grown here in the state. And I put arrows by the ones that are more dominant, and they're on the high end, unfortunately. Our corn, potato, sweet corn, wheat, but you get the idea. And unfortunately, recommendations that are made don't eliminate the risk for nitrate leaching losses out of the soil profile. And a lot of that has to do with sometimes the limited amount of time that nitrogen is actually able to be taken up by crops during the growing season. So in a typical corn agro-ecosystem, you have some nice pictures up there at the top showing the phenological growth and stages through that. There's large portions of the year, if you're not planting a cover crop or something else after that crop comes off, that there's no nitrogen being taken up in the soil, and the leaching potential is quite high for those systems. And as everybody knows, the timing of when fertilizer goes on these systems, farmers are at the mercy of Mother Nature also. The timing of when heavy rains occur can sometimes be untimely and flush a lot of that nitrate through the system. I've had a postdoc in my lab recently, Devendra Threstra, looking at sort of meta-analysis of published studies across the Midwest, including those from Wisconsin, to look at the nitrate leaching coming out of these cropping systems. And this is just an array of those that were highlighted in that analysis that we're getting ready to submit for peer review. And you can see, potato and corn and other systems are on the high end, and then we have some alternative perennials like bioenergy crops, grasses, grazing systems, maybe even hybrid poplar that definitely are significantly lower than those traditional systems. And if you think about the way that the characteristic response of corn responds to fertilizer, it's sort of a law of diminishing returns. That solid line on the top there, represents as you keep increasing more and more fertilizer, eventually you hit a plateau, and you're not really getting that much of an increase in a return. Unfortunately, in our recommendations, the curve on the bottom, that dashed line, is the one that's missing. It's the nitrate leaching response to additional amounts of nitrogen fertilizer being added. And so while the yield plateaus, the nitrogen leaching tends to take either a linear or maybe a curvilinear or maybe exponential increase as you start pushing more and more nitrogen into the system, unfortunately. And obviously, our landscapes and our soils and our groundwater have responded to this over long periods of time. This is just a figure showing private well nitrate concentrations across the state. Some of you already probably have seen this, showing many areas that are greater than the 10 parts per million EPA standard for safe drinking water that's been established. And we understand that there is a close connection between our agricultural management and groundwater nitrate. 20% of the samples that exceed that 10 parts per million standard occurs when more than 75% of the area around that well is cultivated. These types of responses have not escaped the news, obviously. I forget what year it was, a year or two ago, the Governor Evers, declared the year of clean drinking water, to try to get, ahead of this and start doing something about it. And so while it's a local to regional thing that we talk about here in Wisconsin, I want to remind folks that, we are connected to a greater basin, the Mississippi Basin, and then things that we do in many parts of our state make it into the Wisconsin, the Rock, and eventually to the Mississippi. And the hypoxic zone in the Gulf of Mexico, which is attributed to excess nutrients, both nitrogen and phosphorus, has been growing, and the task force has set an overall reduction goal of 45% to shrink the area of the hypoxic zone, with a short-term goal of a 20% reduction by 2025. And you can look at our neighboring states, including our own DNR, and look at the nutrient reduction plans and ideas that are out there and circulating and being implemented as we speak. So on top of, a system of agriculture where we're reliant on fertilizer, I get to come to you on the coldest day in January and tell you about how our weather and climate is changing to warmer temperatures. And that's the way it kind of always ends up being. And I just wanted to review that, overall, the state has been getting warmer, in particularly during winter time, by as much as 5 to 7 degrees over about a 70-year period during the nighttime. Summer, there's a little less certainty. There has been warming, but honestly, the daytime highs during summer have not actually trended much higher, nor have the frequency of extreme heat days like 90 degrees Fahrenheit. In fact, I think the last time it hit 100 degrees in Madison was the year that Dean Kate was hired, in July that year in 2012. It was also 80 degrees in March when you were officially hired then, and everything was blooming. Seasonal precipitation, well, it's been getting wetter and trending a lot wetter. These figures are showing the seasonal increases. The asterisks are significant at the 95th percentile. So we've had significant increases during winter, spring, and summer in many of the agricultural regions. And I wanted to highlight Madison in particular because this directly shows climate change. Each one of those dots that I plotted on that figure represents the 30-year running mean average precip for the city. That increase since the 1970s of almost 25% is unprecedented. The rate at which it's increased and also the amount. And that little list I have there on the bottom right-hand side showing the all-time wettest years in Madison, you might see a trend, 2007, 8, 13, 16, 18, 19. Years ago, I'm sure many of us thought the 1993 Mississippi floods were setting the bar, and that generally just was not the case, unfortunately. And a changing climate is making it harder, to provide clean drinking water in our rural regions. And here's some of the reasons, why. If you think about fertilizer and manure management, it's hard enough to be in farming and harder to be battling Mother Nature all the time. And with increasing amounts of rainfall and an increased frequency of heavy rainfall events, it gets harder and harder to keep nitrogen in the top foot or two of soil where the crop is going to take it up. Soil management, is also significantly challenged. More flooding, we have more erosion. That also compounds phosphorus as it moves in sediment form. So increased rainfall and heavier rainfall events lead to more drainage, more runoff. Warmer temperatures during winter can promote freeze-thaw cycles, which allow for more water to actually infiltrate through the soil. And if you think about warming during wintertime in Wisconsin, the probability of a precipitation event falling as rain versus snow starts to increase also. And so we end up with more drainage and loss of nitrogen stored in that profile. And here are just some of the averages that we had worked up from that meta-analysis. It's grouping those 1,300 data points that were collected into different categories of precipitation, low, medium, and high. And it shows a significant relationship that places that generally have got in years higher amounts of precip generally have more leaching taking place for comparable amounts of fertilizer that are being applied to those cropping systems, these being continuous corn and corn soy. Some of the adaptations that farming, has adapted. These are some pretty interesting publications that have been out. The bottom line is that because of the importance of nitrogen to yield, farmers view that as a threat and a risk that, when heavy rainfalls occur and they're leaching more N out, the response is to add more N to the system to make up for those deficits. And also, if you've been driving around the countryside like I have over the last decade, you've seen more and more pictures like this, more drain tiling being put in places where it doesn't exist. While Wisconsin is not necessarily the hotbed of drain tiling in the Midwest, that goes to Iowa and Illinois and Indiana and the soils they have, we're still trending in that direction, I think, due in response to rising water tables, due to increased precipitation. So what can farmers do to help meet, water quality goals? I want to give some hope for the future, that we can actually start to combat some of these problems. And if we look to our neighbors to the west across the big river, Iowa's nutrient reduction strategy has a nice long list of certain management practices that can be implemented and quantified by the amount of nitrogen load reduction that they can do. And when I stare at this figure and in some of our own research, we realize that simple adjustments to nitrogen management are not going to allow us to get to a 40 to 50% reduction that we really need to help to improve. If you look at some of these on the figure, it's large scale, it's big changes in the system, more pasture land, more CRP land, perennial crops, maybe it's bioenergy. Wetland restoration has been touted as a means to get to 40 or 50% removal of N. But if you look on the bottom there, some of the smaller management of nitrogen itself, side dressing, timing of that, don't really move the needle very far, unfortunately. And so, we need large-scale transformation and a different way of thinking, to achieve those desired load reductions. I just want to briefly cover just some research that came out of my group from Tracy Campbell, who's a PhD student in my lab, collaborated with Eric Booth and Claudio Grattan in entomology and Randy Jackson in agronomy. We performed a modeling study in the Yahara watershed here, where we were able to show that increasing perennials and reducing the amount of nitrogen on the landscape was able to effectively, get to about a 40 to 50% reduction under different types of climate change. And that's the very complicated figure on the right, which I apologize for, but I'm just giving you the punchline here. So it's a transformation and trying to better understand what things can we do to the system to help move that needle that are also going to be economically viable for our farmers. And these are just some of the thoughts, and I would say that Randy is very good at his thoughts of trying to perennialize the landscape, to some extent to combat this. So I just want to leave you with a couple of thoughts. I think we need to develop policies that protect ecosystems and promote multifunctionality in our landscape. Simple adjustments to nutrient management practices will not fix these issues in a short period of time. And I think we need to be getting creative about paying farmers for other ecosystem services other than carbon sequestration or carbon credits. I think water quality is right there for the taking. And lastly, for those of you involved in policy decision making, I would challenge you to think about coming up with more creative policies that eliminate the unintended and negative consequences for ecosystems in a changing climate. We have a variety of US policies dating back to the 1800s that helped promote agricultural expansion in the US. A lot of those had to do with draining wetlands or expanding irrigation, or maybe the renewable fuel standard for that matter. But some of those have led to unintended consequences to people and to ecosystems. And it would be great if we could think more broadly and collectively about food, energy, water systems holistically together when we make policy, instead of treating them separately, because they don't function separately. They function together and are very dependent on one another. So I'll end there. Thank you for listening to me, and I look forward to the other talks.